Hi folks, my name is Philip Lampkin. I am a second year in the Gelman group, and I study Fuldamer photochemistry. One of the things that can be very difficult about photochemistry is that sometimes what you want to know isn't accessible using just experiments alone. In those sorts of situations, you need to be creative, and one of the things that the entire field of photochemistry has come to realize is that computations and computational chemistry can be this really powerful tool to explore systems that might not be easily explored using just experiments. So with that, and given kind of my line of research with Fuldamer photochemistry, I sort of started this new direction inside of our group, which was using computations to determine properties inside systems that we're really interested in. So with that, I kind of want to walk you through some of the resources we have here inside of the department, and I want to show you how to build a simple molecule using these resources and run a very simple computational job on it. This is not supposed to be an exhaustive guide. This is just supposed to sort of show you what sort of simple and easy jobs that you might run should you decide that you want to work on a project like mine. So with that, let's go ahead and let's start. You might note that this looks kind of like intimidating, weird, but actually it's very easy to use. So WebMO, you can kind of think of it like a front end for Gaussian. So Gaussian is the probably premier computational chemistry toolset and like resource out there. Everybody uses it. WebMO is like something you slap on top of it, and it makes it really easy to submit and monitor and also look at completed jobs that you use Gaussian to run. So it was developed. WebMO was developed in-house here at Wisconsin, and it's just the most amazing tool. Even undergrads use it inside our lab courses, just to show you how easy it is to use. So on that note, let's go ahead and start a new job. One of the nice things about this department is that we have a massive computational cluster, which means that it's really easy to submit jobs, and you're never really fighting for space. So on that note, let's go ahead and let's build trans-cinnamaldehyde. The thing that I like to start with is I like to kind of build the single bond skeleton. So I hit the build tool a second ago, and then I started kind of tracing my way around. So that's the benzene ring, and then I'm going to go ahead and build the trans portion of the alkene. I'm going to go ahead and make that into a double bond, and then I'm going to go ahead and add one more, and we'll change that into an oxygen in a second. But first, let's make all the rest of these bonds into double bonds. Almost there. All right, looking good. So now, as I mentioned before, we need to turn this carbon into an oxygen, which means we click this button, and we're going to bring up the element list. So we'll hit oxygen, we'll click on that, and there we go. So now that's looking pretty close, except we're missing all of our hydrogens. Easy fix, we hit this little cleanup tool, and there you go. Now you have a great structure which you can submit to have a job run, and we get the optimized version of the structure, which will be hopefully close to what it looks like inside reality. So we'll go ahead and hit this continue button, and this will bring us to the engine selection. Engine selection lets us pick what sort of computational chemistry toolset we want to use. We're just going to use Gaussian, but one of the nice things, again, about this department is that because we're so big and we have so many computational resources, if you can kind of pick any computational toolset you want to use, we have somebody who knows how to use it, and also it's already set up on the cluster, so it's very easy to use. So for this calculation, we're just going to use Gaussian. Go ahead and hit submit, and this will bring us to the configure job page. If you've ever done any computational chemistry before, you might remember sometimes it can be kind of a pain in the butt to submit a job. Thankfully, with this system, it's all just drop-down menus, and it's super easy to set up. So give it a name, trans-cinnamaldehyde, and we'll go ahead and we'll set it to be a geometry optimization plus vibrational frequency, which basically makes sure that we're going to get a good structure and that it's also a ground state structure, which is important. We're going to change the theory to B3 lip, which is really common for organic molecules. And then we're going to just leave the basis set at a lower basis set 631 GD, which will help the job run relatively quickly. We're going to leave the charge at 0 because this is an uncharged molecule, and we're also going to leave and we will also leave the multiplicity at singlet because this molecule has all of its electrons directly paired. We're going to go ahead and go over to advanced, and to make this job run a little faster, we'll add a few extra cores, which means it'll run on more cores at once, which means it'll get done quicker. And then we'll go over to preview, and if we hit generate, we can see what the we can see what the input file would look like if we weren't using WebMO to kind of make it for us. And as you can see, it kind of looks a little scary. That's why WebMO is such an awesome sort of tool to be used. So we'll go ahead and hit submit. We'll press OK to say it's all right to submit our molecule. And there you go. You'll see that instead of second, it'll go from the queue and it'll start running. And once it's running, it'll run for a few minutes, and it will eventually finish. And then take a look-sees at it. We can see that we have a nice 3D structure once it's done loading. That should look pretty good. But as you can see, we build this nice output, and we see it optimized to an energy level. And we can also see that we have a bunch of vibrational frequencies, which would correspond, say, the frequencies you might see instead of an IR of the molecule. And you also get a great little quote at the end of every single Gaussian file, which is pretty cool. So there you go. That's how you optimize a simple structure like trans-cinnamaldehyde. And this is something that I do pretty often inside the group to figure out things like triplet energies of species I'm interested in instead of exploring. So on that note, if you ever have any questions, you are always more than welcome to send me an email or just sort of yell at me if you see me walking down the street. I would love to share with you about my work, or if you want to ask about different things about the Gelman group, I'm always here. So thank you so much for